Okay, good evening, students. Today we will start with wheatstone bridge circuits. That means in board exams, this type of question is very much important. One or two questions will come from this wheatstone bridge principle only. Okay, so wheatstone bridge principle is very much important, and you all have to know it. Okay, what is wheatstone bridge? Okay, so actually again we were continuing with the things, that is how we can calculate the equivalent resistance of a complicated circuit, and we have done the potential by potential method. Also we have solved the equivalent resistance for complicated circuits, and with the help of that means how we can find out the equivalent resistance for infinitely long register network, that also we have done. So this is now today we will do the wheatstone bridge. That means some circuits are there. It will look like this. This is the circuit, okay? And the current will flow. This is I current is flowing, and this is I1. This is I2. This is I2. Now, the thing is that wheatstone bridge actually is a principle. Wheatstone bridge actually it's the name of a scientist, and he gave a principle, and that is wheatstone bridge principle. And this wheatstone bridge principle, it states that actually the main thing, the main fundamental, the main complex, or you can say the main thing of this circuit is this resistance. Okay. This resistance, the main important thing of the circuit is this resistance. Okay. Now it is said that if the ratio of the resistance in the circuit is equal, that is R1 by R2 is equals to R3 by R4. If the ratio of the resistance in the circuit is equal, then no current will flow through the mid resistance, provided mid resistance R5. No current will flow through the mid resistance R5. This, if the resistance is R1 by R2 is equals to R3 by R4, then there is no current will flow through this branch. Okay? No current will flow through this mid resistance, that is R5. There is no resistance current, that is no current will flow in this branch. Okay? And we can say that Wheatstone bridge circuit is balanced. Wheatstone bridge circuit is balanced. Now, if the potential at this terminal is, let's say, Vx and let's say this is Vy, potential at this terminal is Vx and Vy, then I can say, since there is no current, now see very carefully, please look at this very carefully. At this terminal, at this point, the potential is Vx, and at this point the potential is Vy. Let's say, then if there is no current flowing in this branch, that means there is no potential difference at these 2 points. What Ohm's law says, that if there is potential difference, then only the current will flow. Now, as there is no current flowing in this branch, then I can say this potential and this potential is same. That means there is no potential difference in between these 2 points, in these 2 terminals. There is no potential difference according to Ohm's law. So I can say Vx is equals to Vy. Very important concept. Okay. So what is Wheatstone bridge principle? Wheatstone bridge principle says that if the ratio of the resistance in the circuit is equal, that means R1 by R2 is equal to R3 by R4. That means this R1 and this R2, ratio of R1 by, that is R1 by R2, if R1 by R2 is equal to R3 by R4, the ratio is same, then there will be no current flowing in this branch. That means the potential at these 2 terminals is equal, and then I can say the Wheatstone bridge circuit is balanced. Okay, so this is the Wheatstone bridge principle, and now we have to prove. Wheatstone bridge principle. This is the circuit. Current is flowing, that means I current is flowing, and there is a current division is I1 and I2. The current division takes place. Now, when the current is passing through this resistor, there is a potential drop. If this is V and this is 0, then here actually there is V and there is 0. Now, as the current is flowing in this resistor, there is a potential drop. And we don't know how much it is drop. That means, yes, the drop will be I. That means here actually the potential will be V minus I into I1 into R1. At this point, the potential will be V minus this much is the voltage drop, and here actually V minus I2 R2. This one is the potential drop at this point. Okay. So let's take it as Vx and let's take it as Vy. Okay. Now, obviously there is a potential drop at this point and at this point, and this is Vy and this is Vx, and again the current is flowing. Now, what I will assume, I assume here that, assuming there is no current flowing through R5. There is no current flowing through this branch. R5, through R5 there is no current flowing. That means that is Vx equal to Vy. So if Vx is equal to Vy, then only there is no current passing through the R5. Now I can say V minus Vx is equals to I1 into R1. That means actually what we have proved that Vx equals to V minus I1 into R1. and we have wrote just now we have wrote this, that means Vx, actually Vx is actually potential minus this potential drop, so I can write this. So from here I can write V minus Vx is equals to I1 into R1 from here only. Again we can write Vy equal to V minus I2 into R2. Just now we have wrote that thing. Therefore V minus Vy is equals to I1 into R1. Again there is a potential drop, so Vx minus 0 equals to I1. Now since there is no current flowing in this branch, so here also the I1, that is the current coming from here, there is no division in this branch, so the whole current will flow through this branch. Again the whole current is flow through this branch, so there it is also I2. So it is I1 into R3. Again, so Vx minus V0 equal to I1 into R3. Again Vy minus V0 is equals to I2 into R4. Okay, so Vy minus V0 equal to I2 into R4. So this one is the potential drop. So I can write these things. This is equation 1, equation 2, equation 3, equation 4. These 4 equations I can write. Okay. Now 1 divided by 2 and 3 divided by 4. So what I can write V minus Vx by V minus V5. I can write I1 R1 by I2 R2, and here I can write Vx minus 0 by Vy minus 0 equal to I1 R3 by I2 R4. Now since Vy equal to Vx, so I can write V minus Vx by again V minus Vx equal to I1 R1 by I2 R2. Again here also Vx by Vx equal to I1 R1 by I1 R3 by I2 R4. Now this gets cancelled out. This will be cancelled out. So both is 1. Then from here you can write I can write I1 R1 by I2 R2 equals to I1 R3 by I2 R4. This get cancelled, this get cancelled. Therefore R1 by R2 equal to R3 by R4. This is the proof of wheatstone bridge principle. The simple thing is that the main concept is potential drop, and first thing is that we have assumed that there is no current flowing in this branch. Okay, that means the potential at this terminal is equals to potential at this terminal. Okay, so if I assume this thing, then only we can get this relation, that means R1 by R2 equal to R3 by R4. Okay, so the concept what I have taken there, that means if the potential at this terminal is V, then there is a potential drop and coming as Vx. Again here if the potential is V, then again there is a potential drop and it is coming as Vy. Then V minus Vy equal to the potential drop in this resistance. At same time V minus Vx is actually the potential drop at this resistance. Okay, same, that means Vx minus 0, that means the potential difference is actually the voltage drop at this resistance. Same here also. Okay, so we have get 4 equations we have get four equation of voltage and resistance, and we have just divided this thing and we have calculated this and we have get this relation. That means if the Wheatstone principle says that if R1 by R2 is equals to R3 by R4, then there is no current flowing through the mid resistance. That is mid branch, there is no current flow, there will be no current flow. Then we can simply say that the current is flowing in this branch and transfer in this branch. The current is flowing in this branch, transfer in this branch. So this is series, this resistance is series, this resistance are also series. So and both are in parallel. So we can easily calculate this resistance, this circuits. Okay, and in board exam, actually the main resistance calculation come from this Wheatstone bridge principle only. Based on this Wheatstone bridge principle, we can easily solve the circuit problems. Okay, let's see how we do. So this is the proof of Wheatstone bridge principle, and the proof is also very important. Okay, the question may come that proof of Wheatstone bridge principle and proof relation also. Okay, so this thing is very much important. Let's take some of the question. Okay. Okay. Now tell me, what is the equivalent resistance of this resistance of this circuit? Okay. So what we have to do? Again, we have to take this as V voltage and this is series. So at this terminal there is V voltage, and at this terminal there is zero voltage. Okay. Now, so there is a current flowing in this bunch like this. So there is a current division. That means here some current will go I1. Here some current will go I2. Obviously, the current will flow in this branch, and there is a resistance. There is a potential drop in this resistor, and let's say at this terminal the voltage will be Vx let. Again the current will flow in this resistance, and let's say the voltage will be Vy. Okay. So at every terminal we get the voltage, and now draw. This is V0 terminal. Sorry. This is V terminal. This is 0 terminal. Let's say take it as Vx terminal, take it as Vy terminal. Now this resistance is connected between V and Vx terminal. So this resistance is actually this resistance. This resistance is actually drawn like this. Now take it as this terminal, this resistance, it is actually connected with Vx and 0. Vx and 0, this resistance is connected. Draw it. Now, see, this resistance, it is connected with Vy and 0. This is Vy and 0, so we have to draw this resistance. Now, this resistance it is connected between V and Vy. V and Vy, this resistance have to connect. Now, this resistor it is connected between Vx and Vy. So this resistance it is connected between Vx and Vy. So everyone is So now it is looking like wheatstone bridge circuit. Now here R1 by R2 equal to R2 by R4. That means what wheatstone bridge says that R1 by R2 equal to R3 by R4. Now see, R1 is also R, R2 is also R, R3 also R, R4 also R. So that means R by R equal to R by R. That means it is minus 1 equal to 1. That means the relation is valid. That means there is no current flowing in this branch. There is no current flowing in this branch. That means the equivalent circuit will be like this. Okay, then that means R equivalent will be 2 R by 2. That means R. So R equivalent will be R. Okay, so this is actually how we have to solve wheatstone bridge principle. So it is actually a wheatstone bridge principle. Now take another example, the last one. So this is the equivalent resistance. Okay, so this is the equivalent resistance, and you have to find out the how you have to find out. Okay, now see, as this type for this type of terminal, you have to again connect a battery. Let's say this is V and this is T. Let's say. So what will happen? Here actually the V and here actually the 0. Now again this branch there is no circuit element. So this is also 0, this is also 0. Understand? Now see, this voltage there is a current flowing. Okay? Again when the current is flowing in this resistance there is a voltage drop, and let's say this is Vx. Let's say. So if this is Vx, then this point is also Vx. Again there is a current flowing in this resistance, and again the voltage drop is there. Let's say this is Vy. Okay. Now this current is flowing, so this point will be again V. There is no circuit element in this branch, so this this point is the potential and this terminal is also V. Okay. So again we have get the 3 points, that means one is V, another one is 0, this one is Vx, this one is Vy. So this resistance, it is connected between V and Vx. So this is now see this resistance it is connected between V and 0. So it is connected between V and 0. V and 0. This resistance, it is connected between Vy and 0. This is Vy and 0, and that means this resistance is connected between Vy and 0. This resistance, it is connected between Vx and 0. This Vx and 0. That means this resistance, it is connected between V and Vy. V and Vy, this resistance is connected. And this resistance, it is connected between Vy and Vx. So this is also looking like a wheatstone bridge circuit. Okay. So this is actually a wheatstone bridge circuit. Okay. So you see here also the wheatstone bridge balancing condition is satisfied. That means R1 by R2 is equals to R3 by R4. So there is no current flowing in this branch. There is no current flowing in this branch. So I can consider this as this one is these two resistors are in series. These two resistors are in also series, and these two branches are in parallel. So the equivalent resistance, so that means the equivalent circuit will be like this. That means two R here in parallel. That means ultimately R equivalent will be, if you calculate, then it will be R by 2. So let's see. So this is the actual answer. That means for this circuit, this type of circuit, the R equivalent will be R by 2. So see, this is actually, it is, if you look like this, that means it is not looking like a wheatstone bridge principle. Now, if we apply that potential method formula, that means if we apply the potential method technique, then we can find that this actually a wheatstone bridge principle. Okay, this actually the wheatstone bridge principle. It is very much important. Potential method is very much useful. It can be useful in any type of circuits. Okay. So potential, actually this is actually wheatstone bridge principle or wheatstone bridge circuit, and we apply the wheatstone bridge principle and we can easily find out that the R equivalent is R by 2. Okay. So this is actually the wheatstone bridge principle, and just practice many such circuits. Okay, in your book only you have many circuits. Okay, practice that, because this type of question will come in the exam. Okay, and very much important. Okay, thank you.